In this video, we'll define a Cauchy sequence. A sequence AN is called a Cauchy sequence if, for every epsilon greater than 0, there exists a big N in the naturals, such that whenever m and n are greater than or equal to big N, the absolute value of am minus an is less than epsilon. And at first glance, this looks very similar to the definition of convergence, except there's one notable thing missing. There's no limit. So this is a different quality about sequences. In the definition of convergence, we say that for any epsilon greater than 0, there exists some point far enough out in the sequence such that all the terms at or beyond that point are within epsilon of our limit. This is saying something a little different. It's saying that for any epsilon greater than 0, there exists some point in the sequence such that beyond that point, any two terms are within epsilon of each other. And this holds for all epsilon, just like in the definition of convergence. This is a stronger condition than just saying that differences between subsequent terms tend towards 0. But it certainly implies that. What we'll prove in this video is that a sequence of real numbers is convergent if and only if it is Cauchy. That this is actually an equivalent condition to convergence. And that'll give us a nice way to demonstrate the convergence of certain sequences without needing to find the exact limit. Let's first prove that every convergent sequence is a Cauchy sequence. So let's assume that a sub n converges to some limit L. Reminding ourselves of the definition of convergence, this means that for any epsilon greater than 0, there exists a big N in the naturals, such that for all little n greater than or equal to big N, the absolute value of a sub n minus L is less than epsilon. So we'll be able to choose whatever epsilon threshold we want in this definition, since we already have the convergence of the sequence. What we're trying to demonstrate is that the sequence is Cauchy, meaning for every epsilon greater than 0, there exists a big N in the naturals, such that for all m and n greater than or equal to big N, the absolute value of am minus an is less than epsilon. The basic idea of the proof is that if we can go far out enough in the sequence such that all the terms are close to some limiting value, then they must be close to each other. Let epsilon be greater than 0. The same line that starts our convergence proofs also starts our proofs when showing something's a Cauchy sequence. Now to take two terms to be within epsilon of each other, we can't just take them both to be within that same epsilon of the limit, because then they could be up to 2 epsilon apart. So we'll take them each to be within epsilon over 2 of the limit, and that'll force them to be within epsilon of each other. On a number line, that's just because they lie in this same interval, which only has a total width of epsilon, but algebraically, this will be justified by the triangle inequality. And we're really starting to see lots of examples now of where the triangle inequality is useful. Whenever you want to make two values close to each other, and you know they're both close to some third value, you can apply the triangle inequality. Let's continue our proof. By the definition of convergence, there exists a big N in the naturals, such that for all n greater than or equal to big N, the absolute value of an minus L is less than epsilon over 2. And now we can keep the same choice of big N and say, for all m and n greater than or equal to big N, the absolute value of am minus an, that's the thing we need to make small, is equal to the absolute value of am minus L plus L minus an. That's the setup for the triangle inequality. We're connecting the difference between am and an to the two differences between am and L and an. Is less than or equal to, by the triangle inequality, the absolute value of am minus L plus the absolute value of L minus an. And the order of those terms doesn't matter because they're all inside absolute values. And each of these we've taken to be less than epsilon over 2, and so the whole thing is less than epsilon. Now we'll turn our attention toward the reverse direction, that every Cauchy sequence is convergent. And this will be a little trickier to prove, because in order to demonstrate the convergence of a sequence, we need it to have a limit. So we'll start with a simpler statement. Lemma, every Cauchy sequence is bounded. Let a sub n be a Cauchy sequence. We'll complete this proof using a similar technique to ones we've seen before, where we have two parts of the argument one to control the infinite tail of the sequence, and one to control the finitely many terms at the start. Because we want to be able to take a maximum of all terms in absolute value and say that has to be a bound. But the reason you can't do that generally is because you could have an infinite tail that goes off to one infinity or the other. But with Cauchy sequences, we're guaranteed that for any epsilon, there exists a big N such that all the terms past that point are within epsilon of each other. And so let's just choose epsilon equal to 1. Then there exists some big N in the naturals such that for mn greater than or equal to big N, the absolute value of am minus an is less than 1. So let's specifically use the index big N as one of those possible indices greater than or equal to big N to say that for all n greater than or equal to big N, the absolute value of an minus a big N is less than 1, which implies that the absolute value of a sub n is less than the absolute value of a sub big N plus 1. And this is one of those statements that I think is intuitive enough if you draw a number line that I don't need to justify it algebraically. But if you wanted to, you could. You could use the normal triangle inequality in some manipulations, or you could maybe more directly use something called the reverse triangle inequality. I'll leave that as an exercise for you to think about and maybe prove this reverse triangle inequality. But returning to our main argument, we now have a bound on the infinite tail of our sequence. It's not guaranteed to be a bound for all the terms with an index less than big N, but that's only finitely many terms. So we'll set big M equal to the maximum of the absolute value of A1, absolute value of A2, up through the absolute value of AN minus 1, comma, the absolute value of A sub big N plus 1. And then we're guaranteed that big M is a bound for the entire sequence, and thus the sequence is bounded. Stating the second half of our main result, every Cauchy sequence is convergent. Let A sub n be a Cauchy sequence. By the lemma, A sub n is bounded. The reason we need this lemma is because we'll need a candidate for the limit, and now we'll have one using the Bolzano-Weierstrass theorem. That theorem that we proved last video states that every bounded sequence has a convergent subsequence. So now we're guaranteed that A sub n has a convergent subsequence, and let's say that it converges to some limit L. Now we're going to try to argue that the whole sequence A sub n has to converge to that limit L as well. The reasoning will be somewhat similar to proofs we've seen before, where we argue that two things are close together by arguing they're both close to some third thing and applying the triangle inequality. Let's let epsilon be greater than 0. Now we need to show that there's some point big N in the sequence such that all the terms beyond that are within epsilon of L. Since A sub n is Cauchy, there exists some big N1 such that for mn greater than or equal to big N1, the absolute value of am minus an is less than epsilon over 2. We'll use epsilon over 2 to give us an extra bit of wiggle room to fit in the difference between our terms of the subsequence and the limit. Now, the subsequence guarantees that for any epsilon threshold, there's infinitely many terms of the original sequence within that epsilon threshold. They're just not guaranteed to all be next to each other. They could be spaced out. But we actually don't really need infinitely many. We're just going to need a single main term that we can use to connect all the other terms to the limit. Let big N2 be a natural number that's greater than or equal to big N1, such that the absolute value of A sub big N2 minus L is less than epsilon over 2. And we know such a big N2 exists because a subsequence of AN converges to L. Now we're going to write down our main statement demonstrating what we need to show. And we need to choose our specific big N. I'm going to use big N2. For any natural number n greater than or equal to big N2, the absolute value of A sub n minus L is equal to the absolute value of A sub n minus A sub big N2 plus A sub big N2 minus L is less than or equal to the absolute value of A sub n minus A sub big N2 plus the absolute value of A sub big N2 minus L, and each of these is bounded by epsilon over 2, the first because of our Cauchy condition, and the second because of that subsequence convergence. And so this total is less than epsilon. It's very satisfying to write down the final line of a convergence proof, where all the pieces you've set up ahead of time come together in one final slam dunk. And so altogether, we now have that a sequence is convergent if and only if it is Cauchy. This foundational understanding of sequences of real numbers that we've established in the last several videos will serve as a foundation for a lot of things that we're building towards. Like, for example, a little later on, we'll discuss sequences of functions instead of just sequences of numbers. What we'll use them for in the more immediate is as the foundation of our discussion of infinite series. In my opinion, one of the most fascinating mathematical objects.